All right, we are moving on to 9.3a. The next worksheet, which I believe we'll do Thursday, we are going to be counting and eating Skittles. Unless you would prefer M&Ms. Skittles? How many of you want M&Ms? How many of you want Skittles? Skittles it will be. Okay. And Garrett, I've talked to Tawny. She's going to get you some Skittles, I believe.
Yeah, let's go. All right.
Okay. Plain. Plain. Plain M&Ms are gross. Hershey's chocolate is not very good, but the peanut butter M&Ms, those are yummy. But I don't have data on peanut butter M&Ms, so it won't work. But okay. Anyway, 9.3a. We are going to do a chi-squared test for goodness of fit. Oi, look at you guys. You are just not paying attention to me today. I am the most important thing in your life right now. So, chi-squared goodness of fit. So we're going to look at a situation and we're going to have some assumption on what is going to happen, and then we take a sample and we compare that sample to what we thought was going to happen using a chi-squared test. Okay? And there's actually another chi-squared test, and as far as I can tell, it's not in the book. So I don't know if we'll get to that one or not, but whatever. Okay, so principal surveys 150 students to determine their favorite academic subjects. The results are, shoot, I need to add something in here. It is assumed that all categories are equally popular. I need to add that to, or it won't make sense. Okay, so we ended up with 42 students who chose math, 38 that chose science, 25 chose English, and 30 chose history. So we have multiple categories. We want to test multiple categories at the same time. So we can't do a one sample test. We can't do a two sample test. We have 4 samples. So that should tell you that you're going to do a chi-squared test. Now, the chi-squared test has a, what do they call it in the book? Anyway, there's a requirement. Do you remember from 9.3 in the Zai book what the requirement is? At least 10 results in every category. So the first question, do we have sufficient data to run a chi-squared test? Yes. Why? We have at least 10 in each category. If you don't, then you have to use another test, and guess what that test is? I have no idea. Never learned it. Okay. So for each category, we have to calculate the expected value. So what is our assumption? Our assumption is that that each subject is equally liked, or the same number of kids like each subject. So there are 4 subjects. So if everything is equal, what would we expect in each category? It would be 25% of 150. So 50 divided by 4 is 37.5. So we would expect 37.5 in each subject. Now that's not always going to be true. When we do our Skittles, are we going to assume that there are just as many reds as there are oranges? And the answer is no. They're not the same. Okay, so what are the null and alternative hypotheses for this test? So our H naught is going to be, are we doing pi or are we doing mu? These are proportions. So the pi for math is equal to the pi for science, which is equal to the pi for English, which is equal to the pi for history. So that's the first half for number 3. And then what about the second half? At least one is not equal. So that would be at least, I guess, well, I think the book said 1 pi is not equal. And we need a method to test all of these at the same time. So we could go through and compare 1 to 2, and then compare 1 to 3, and compare 1 to 4, but not only would that take a lot of time, it doesn't do a good job of comparing everything the same, because a change in science will affect math and so on. So we need to be able to check all of them at the same time. Okay? So what is the chi-squared statistic? Well, we need to calculate, oh shoot. Oh, no, we're good, never mind. So the chi-squared statistic is going to be the difference between the expected value and the observed value squared divided by how many you expected in each category. Right? So it's going to be 42 minus 37.5 squared divided by 37.5. And for simplicity's sake, I'm always going to list the big number first to avoid the negatives. The squared is going to take care of the negative, right? So that is the first term of our chi-squared statistic, plus, next one is going to be 38 minus 37.5 squared divided by 37.5. Plus 37.5 minus 25, that'll just make it easier for me to do in my head. 37.5 and square that. And then 37.5 minus 20, minus 30 over 37.5, and I'm going to square that. Okay? Yeah, not fun. So I plug that in my calculator. So I get 5.5 squared divided by 37.5 plus 0.5 squared divided by 37.5 plus 12.5 squared divided by 37.5 plus 7.5 squared divided by 37.5. Okay, I hope somebody else plugged this in. Did you get 6.48? Yeah? All right, that is our chi-squared statistic. It's like a t-score or a z-score, and we need to use our table to figure out what that means. Okay? Yes. So we're assuming that every category is equal, and there are 4 categories. So if that's true, if the null is true, then 1/4 of the student should choose math. And 1/4 of so 150 divided by 4 is 37.5. And it's actually going to be quite different on the next one. So that's a good question. Every category is expected to get 37.5. But that's not always the case. All right. So scroll down. No, I'll scroll down. How about you look at your back page? Okay, degrees of freedom. In a chi-squared goodness of fit test, the degrees of freedom is simply, are you still confused, Blake? What do you need? Oh, Blake. So the degrees of freedom are the number of categories minus 1. So we have 4 categories. We subtract 1. Our degrees of freedom are 3. So we have a chi-squared value of 6.48, and our degrees of freedom are 3. So we look at this row, and we go across until we find 6.48, which would be somewhere between 10% and 5%. So our p-value is, let's do it this way. Our p-value is somewhere between 10% and 5%. So would we accept the null or reject the null? We would accept it, just barely. And a lot of times the Xi book says, yeah, it makes us nervous. You reject the null if your p is less than 5. And our p is bigger than 5. So do we really trust that these numbers are the same? We're on the verge of rejecting, but it wasn't enough to reject. Okay? Yes? No, you square each individual term. That's a great question. So let me show you. So let's go to your Xi book and I'll show you the formula. So 9, 3. So here's the formula, right? Not that one. Come on, there it is. So the formula says, take how many you had minus how many you expected, find the difference, and just so I could make it easier in my head, I always put the big one first. Square that and divide it by the expected, and then line that up for every category. So this one had 1, 2, 3, 4, 5, 6 categories. So for this one, the degrees of freedom is going to be 5. So if I wanted to look this up, my chi-squared is 16. So I go to my table, and I go to row 5, and I find 16, which is way over here somewhere. So what is my p-value? Less than 1%, so do I accept or reject? We would reject the null. Does that mean yes or no? It depends on the question. Right? Depending on how the question was asked, it could be a yes or it could be a no. Okay. Now, I don't know how they're going to ask this question on the final, so I do want to show you this. So everybody log into the Rossmann One Chance. And as far as I can tell, there is no way to just plug the numbers in and then have it spit out a chi-squared test. But if you know the degrees of freedom and you know your chi-squared statistic, there is a graph that will allow you to check that. So if we, I think it's right here, probability calculators. So right there. So if you click on that button, and then, well, our degrees of freedom were 3. And then what was our chi-squared? I erased it, 6 point something. So go here, and it's right, it's the very end of the probability calculator. Is it not showing up for you guys? Oh. Sorry. You have to push the updated 2021? Okay. All right, did everybody get there? So we go here, we go there, and we're going to type in 3. So we type in 3 there, and we type in 6.4 And then we have to shade, we want to go greater than. So what is our p-value? 9%. Is that what we got when we looked at the table? Yeah. So my recommendation is look at the table, because on the final you might only have a table. I'm not sure how they're going to ask that question. So look at the table, answer the question, and then go into this and plug in your numbers, and you'll get that. So for the one that was in the Xi book, the degrees of freedom were 5, and the test statistic was a 16. And we should get a p-value less than 1. And there it is. P-value less than 1. Okay. Now, this is a little bit weird because is this a one-tailed or a two-tailed test? Well, it sort of looks like a one-tailed test because we want to know, are they all the same or are some of them different? But we're not graphing on a normal curve. This chi-squared is always going to be right-tailed. And we're always going to be testing greater than. So I don't even believe there's an option for equal to. So we're always going to test greater than. We're always going to shade the right tail. Okay, and then that table I printed off for you, that is a right-tailed chi-squared test. I don't even know why this has a left-tailed. Like, that doesn't make any sense to me. All right, let's do the next one together. This one's a little bit tricky. Okay. A researcher surveys 100 households in a neighborhood to determine the types of pets they own. They want to see if the pet ownership distribution matches the national average. Go away. For pet ownership. So we're assuming that dogs are 35%, cats are 30%. Oh, that doesn't work. Guess who needs to update this? I deleted 2 categories. So that adds up to 65, 72. So change this to 72. And then, how about 77? When Blake corrects me, you know I made a mistake. All right, so let's say 35, 30, that's 75. Okay, so let's do 45, 40, and 15. So change that to 45, 40, and 15. Yeah, there were 2 categories, but I wanted an easier problem, so I deleted them. All right, number 8. Do we have sufficient data to run a chi-squared test? Yes. Why? We have at least 10 entries in every category. Okay? So now, what are the expected values for each category? Are we expecting that they're all going to be equal? No. So how do we figure out how many dogs we expect? You're going to take 45% and multiply it by the 77 from your sample. So 0.45 times 77. So we expect for dogs, oh, wrong one. Dogs we expect 34.65. Cats, so 0.4 times 77 is 30.8. And birds, so 0.15 times 77 is 11.5. 55. Okay, does everybody understand that? Anybody confused where those numbers came from? Oh, so the last one, we assumed they were all even. Right? Yes. So really, The last one was 37.5, 37.5, 37.5, 37.5. We just didn't write them all down because they were assumed to be even. Like if you're rolling dice, you would assume the number of ones to be equal to the number of twos. But if you were picking favorite animal, are the number of bird likers the same as the number of dogs and cat likers? No. So we need to, our formulas need to allow for that. Okay. Okay. Any other questions there? Has anyone ever had a bird? They're horrible pets. They're so loud and annoying. And they just don't taste very good. Not like a cat. All right, so what is the null and the alternative hypotheses? Are we going to say that pi d is equal to pi c? No. So what we do is we say h naught is that pi d is equal to 0.45, 45%. And pi c is equal to 40%. And pi b is equal to 15%. Okay? And I guess you could use the numbers too. If you want to say pi d, not pi d, but I guess you can't because that's not a percentage. So you do have to use pi. What would the alternative say? At least one is not the same, is not true. So our alternative hypothesis, HA, says at least one is not true. One of those proportions. Okay. Everybody good? All right. So the chi-squared statistic is the same, but you have to be careful because your denominator is going to be different for each category. You always divide by the expected. So our chi-squared statistic is going to be 34.65 minus 30 squared divided by which one? Nope, you don't use percentages, you always use counts. 34.65. And just to remind you, here it is. So look at this formula. The formula says the number you had minus the number you expected squared divided by the number of expected. And again, I always put the big one first so that I can do that math in my head. If I can, I guess. It doesn't always work out. Okay. So what's the next term going to be? Plus, help me out. 12 will be the last one. So 35 minus 30.8 squared over 30.8. Okay, Taylin, what's the last one? 12 minus 11.55 squared over 11.55. And so let's type this in. So the first one is going to be 4.65 squared divided by 34.65 plus. The next one is going to be 4.2 divided by 30.8. And then the last one is going to be 0.45 squared divided by 11.5. Okay, any questions? So we hit enter. and I get 1.214. So my chi-squared is 1.214. How many degrees of freedom do we have? Yes?
So why do you have 34.69 first for the first one? All the rest is second.
It doesn't matter. I just was avoiding negative numbers. But good point. I mean, you can switch because we're squaring them, the negatives are going away. So yeah, I just do that because it's easier. I've only said that 4 or 5 times. So. Okay, so how many degrees of freedom do we have? 2. So we go to our chi-squared paper. All right, we look at this. And we go to row 2. Where is 1.21 on row 2? It's somewhere, so we look here, it's somewhere in there. So it's somewhere between 90% and 10%. Right? There's a huge gap right there. Okay? So our P is greater than 5%, which means no, 1.21. Yeah, not 0.121, 1.21. So my P is greater than 5%, so what's my answer? We accept the null, which means we what? They're not all equal. They all fit within the expected range of the national average. Okay? Now, plug those numbers into your chi-squared calculator and see if you get the same answer. We're going to go in here. So we're going to change this to a 2. And we're going to change this to a 1.21 and run that, and I get 54%. Is that what we expected? Yeah, that's the same value. Well, we had somewhere between 90% and 10%, and 54 is somewhere in there. Okay, questions? So you would need to say our p-value is greater than 5%. So you would say, because our p-value is greater than 5%, we accept the null hypothesis, which means our numbers match the national average. So our p-value is greater than 5%, which means we accept the null hypothesis, which means our results are not significantly different than the national average, or you can say they're the same as the national average. All right? Okay, get to work.